Thank you. Sorry I couldn't be with you today. So, and thank you for the very kind introduction. So I thought I would talk a little about cities and energy from a multi-scale systems perspective. So, we're very interested in cities because of the well-known now urbanization trends and the fact that, most of the population growth we're seeing from today and into the future is essentially an urban population. And so we see, not only are cities interesting, but cities are in constant flux. So this is just showing a size rank graph, which shows how some of the um, real growth in cities is in the lower and middle income countries, where not only is there an opportunity to look at the growth of the city and the expansion of things like infrastructure and energy, but also opportunities to rethink city architecture and, of course, infrastructure architecture, because there's no reason to follow the trajectory that we've followed, for example, in the north and west. What's interesting, of course, is that we focus a lot on megacities because they have a very high profile. But actually, when we look at the population distribution in the left graph, we actually see that most people actually live in small cities. And I think that's quite interesting because from the point of view of systems engineering, planning, the kind of interventions we'd like to make in sustainable cities, it means that they're probably more amenable to practical action. And actually, when we think about the mega cities, for example, in red, they actually fragment typically into polycentric clusters anyway. So dealing with that blue band of small to medium cities is probably where our biggest wins can be. One interesting thing about how energy use develops with urbanization is not only are we seeing increased urbanization in the low and middle income countries, but actually because of higher disposable income and better access to technical energy, we also see that a Beijing or Bangkok city dweller uses 3 times as much energy as the Chinese.
So, as you can see, the other thing we think about in urban form, of course, is that every city is quite distinct and architecturally different. But when we look at it from the engineered systems that we have to deal with, we see the same challenges of infrastructure. So that's energy, waste, water, transport, built environment, and so on. And once we start to see that kind of modularity in systems, it starts to make us think that cities might be amenable to systems approaches. So one challenge we have from an energy point of view is cities are inefficient. So they absorb, if you like, upstream and within the city a large amount of primary energy, and a lot of that ends up being wasted. And for those of you who like thermodynamics, we can look at it from a perspective of first law of thermodynamics, where we see a city might be about 50% efficient. 50% of the energy that is somehow associated with the city is providing some useful service. And for those of you who like to look at second law of thermodynamics, it's even worse. If we look at exergy, we see that cities might only be 18% efficient. So, what can we do? And I think one of the big challenges we have is that our whole economic system has been driven by the advances from the 18th century onwards of the Industrial Revolution. So historically, what we're showing in this graph is how cities in pink are a locus of energy consumption. So the x-axis is showing the size of the city, and the y-axis is showing the energy intensity in watts per square meter. So historically, cities relied on the hinterland that's shown in green, particularly photosynthesis. So, we drove our economic development up to the 18th century with primarily biomass, a little bit of water power for mills, a little bit of wind power for mills. What happened then in the Industrial Revolution is we got access to the energy sources that are in grey, which have a much higher energy intensity. So we've got much higher watts per square meter when we're using these energy dense fossil fuels and the associated technologies like thermal power plants. And that, of course, drove huge economic development. It drove huge population growth. It drove urbanization. And now, of course, the challenge we have is we're saying, how will we have a transition where we'll start to phase out some of the things that are in grey and go back to the things that are in green and have these big energy hinterlands for cities. And what we really need to do then is look at, can the energy density provide opportunities to make cities more efficient? Because, if you look at this efficiency, it's also an opportunity. But I think this picture shows the challenge, because in a way what I'm saying is, if we're not careful, we have to go back to how life was in the 18th century if we're going to start to wipe out everything that's in grey. So of course it's a much wider problem than just cities. It's about our industrial and our transport and agricultural systems as well. So I think this shows the big challenge of the energy transition, but also the potential opportunity from energy density point of view. The one challenge we do have, of course, is that energy density provides these opportunities, but that requires what we call systems integration. That means thinking about different aspects of our urban system and integrating them. But that's often very difficult, because that's actually something which relies on policies that are often fragmented. So a transport policy, a buildings policy, a waste policy, an energy policy, they don't tend to be joined up. Nevertheless, what we've been looking at in our approach to cities is a 4-level systems-based hierarchy, where we look at the bottom level. How is the city organized? What is the economic activity? What is the land use? What are some of the natural features and characteristics of the city? Then at the next level, how do those 2 or 3D characteristics of the city influence how people behave and how they use the city? Then in the 3rd level, we have the resource flow. How does that behavior and that land use influence demand for energy services, and how can we supply them? And then finally, at the top level, what is the smart system that can help operate the city effectively? So we're really interested in 2 main questions. How does resource demand arise from the land use, from the behavior, from the technologies that we have? And then how do we supply those resources in the most effective and perhaps low carbon way? And so I think what's interesting about how we've been trying to look at this systems-based approach is not to start from the point of view of, we need a smart city, which is often how people perceive this problem. Let's make everything smart. No, for us, it's really the smart system needs to be conceived in the service of some fairly sophisticated understanding of the city and its different elements. And so you're not just adding smart onto maybe what was a very dumb system. So I'll talk a bit about these in turn. I'll start with how we think about land use and built environment. And really what we're quite interested in is the opportunities for planning of existing cities or planning of new cities or rezoning cities. So this is just one example, and actually in a few slides I'll show a bit more about how we model things. But here what we're looking at was a design that we were working on with a developer for a so-called eco-town in the UK. And those numbers in the cells are the housing density. So those are the dwellings per hectare. And this was a kind of original design, which was already a low energy design. It's about less than 1/3 of the energy consumption of London, according to this design. The L are the leisure facilities, and the S's are some mixed-use developments. And so we went through some different design options. The developer asked us, can you develop a very low energy? What's the lowest energy design you can come up with? And we came up with this design where we left a lot of green space. We had some leisure facilities, but we ended up, showing a high density design. So you can see the 65 indicates much higher density, a bit more like a maybe Asian type of city. And they said, yes, very interesting, very low density, but we're actually trying to sell these houses to people. They're not really going to want to live in a place like this. Can you redesign, and can you also make schools and other facilities a bit more accessible to people? And so we went around a few iterations with them, and we came up with this kind of 2-node design. So a south western node and a northeastern node separated by some green space. And in each case, through detailed modeling, we can estimate our energy consumption. So this is our kind of lowest level of the hierarchy. This is obviously an extreme example where it's a greenfield site. It's a completely new town being planned from scratch. So you can actually look at different urban designs and you can use them to estimate what is the per capita energy consumption. So that's an unusual case. More common is the case where we have a kind of existing design and we're looking at how do we supply the energy and related services in the most effective way. And this is the level of the system that is most common and probably, no doubt, also subjects to some of the presentations in your event. So here what we're looking at is modeling of an urban environment where we look at 5 key elements. The spatial element, how the space is organized. A temporal element, how people require energy services over time. Resources, so different kind of resources that are related to energy. Technologies, again, different technologies which are related to energy. And infrastructure or networks, so things that move resources. So let me say a few words about each of these. So the spatial element, we look at a cellular representation of the urban environment. That can be an abstracted cellular environment like the top right, or it can be a very faithful one with shapes that are reflective of the particular parcels of land as in the top left, or a kind of hybrid as the bottom right, which is a cellular representation of United Kingdom when we're looking at some energy modeling of the whole country. So these cells can have, of course, characteristics in terms of the shape, the size, and various information like the land type, land cover type that's there, what kind of built environment, any existing technologies, population, demand, and so on. So we need a spatial representation of our urban system. Then we need a temporal representation, and usually our temporal representation has multiple levels in a hierarchy because, of course, we have energy demands varying by season, but then we expect to do some planning of our urban environment, so we have a long time scale for infrastructure changes or changes in the built environment. But then, of course, we have humans that have behavioral patterns, they have weekdays and weekends, and they have different kind of activities through the day. So we're trying to capture how cities operate on a multi-timescale basis. Then our next key element in our modeling framework is resources. So our resources include things like energy resources, natural gas, electricity, biomass, petroleum, but also wind and sun. And then we have our demands, which might be supplied by these end-use energy vectors like electricity, heat, transport fuel or transport energy. We also include wastes as notional resources because sometimes there are opportunities to access these wastes and use them. And finally, we have our technologies. So technologies can be large scale, like a nuclear power plant or a waste to energy plant. They can produce multiple outputs like heat and power, or they can have multiple inputs like low-grade heat and electricity. And they can have multiple operating modes. And sometimes you have different scales. You can have a household boiler or, of course, a large-scale district heating boiler. And they interconvert these resources from input resources to output resources. So then we look at a system optimization model, which includes questions like which resources should we use in this city, which technology should we buy, what scale should we buy these, where should we put them, when should we install them, what networks should we build to connect the different elements of the city, how resources should flow. Then, of course, we have constraints like resources must balance, we must meet the demand for energy services, we must meet some cost constraints, hopefully also meet some greenhouse gas targets. And of course, we can't change our urban systems overnight. So we have build rate constraints, so constraints on how quickly you can build infrastructure, install technologies, either at the household level or at the district level or at the city level. And once we put all these together, we can come up with some interesting system designs. So here's one interesting example, which was not in Europe, it's in China. It's called Lingang New City. It's a study we did with the municipality there. So they wanted to make this one of China's no-coal cities, to be good air quality and lower GHG consumption. It's a four-zone city, so there's a main city in the southeast. There's a mixed-use zone in the northeast, main industrial area in the northwest, and a heavy industry area in the southwest. The climate is quite interesting in this part of China. It's actually very hot in summer and it's quite cold in winter. So it needs cooling in summer and heating in winter. And they have some nice technologies in China, like what we're showing in the left is a large-scale district-level gas engine heat pump. It's reversible, so it can run in heating mode in winter and in cooling mode in summer. It's a ground heat interchange system, so it will dump heat in the summer underground and it will abstract heat from underground in the winter. And the prime mover is a gas engine, but it runs in heat pump mode, not as a boiler. And so these technologies that they're developing in China, they were quite interested in also not only how to have a low carbon city, but how to deploy latest state-of-the-art technology that was being developed in China. And then they also have building level heat pumps and building level cooling systems. And so you can actually integrate these with the network. And so what we come up with is a dual flow multiple node network. So we have our 4 city nodes. Those 4 nodes are all served by a dual flow network that provides heating in winter and cooling in summer, and which is primarily driven by large-scale gas engine heat pumps. Instead of the 4 zones being completely independent, they're actually interconnected, which provides some system balancing between day and night and different types of users, and also some resilience to any failures. So that's, if you like, the system design and network level, but we're also very interested in the smart systems and actually, real-time operation. So here we're looking at a challenge that we particularly face in cities like London, but I'm sure, I think in Switzerland it will be very similar, where we have space heating demand around 21 degrees. We're currently using a lot of gas boilers, which is really an inefficient way of supplying heating. But also we're increasingly finding that our economy in a country like the UK, which has gone from an industrial economy to a service economy, is requiring a lot of cooling. So we have very, very large increase in data centers. We have very large increase in other types of environments which require cooling, including substations, our underground system, other kinds of commercial buildings, such as retail. And so what we have here is an ability to take the waste renewable heat from those cooling demands and use them to integrate within a heat network, but actually, exploiting the fact that a lot of our decarbonization of heating, moving from boilers to heat pump, actually creates cold dumps, if you like. So, if you think of what comes out of a heat pump on one side is actually cold. So, for example, when we abstract heat from the air or the ground in a heat pump, we actually create a cold stream. So is there a way of actually integrating that with the users of cold, like data centers? And the other thing, of course, we now have is much better heat pumps with controls and much better control systems. So what we're looking at here is the idea of a heat autonomous city, where we have heat and cold networks that integrate cooling systems that are generating waste heat and heating systems that are generating waste cold, and then system balancing with heat pumps and chillers. And so what we have is a system a bit like this, where we have a cold loop at the bottom and a hot loop at the top with reservoirs or sinks, and then everybody who needs heating can take from the hot loop and everybody who needs cooling can take from the cold loop, but the hot loop actually provides cold to the cold loop and the cold loop provides heat to the hot loop. It's an abstracted system, And I can show you, this is what more the engineered system, how it looks. So we have a hot side and a cold side, and we're now considering a project that we're working with our partners who are operating and designing a lot of data centers in a new part of London, and looking at how we might actually practically design and implement a system like this. So we're going from an abstracted system, which looks, well, we're coming from a problem statement, if you like this, to an abstracted system, which looks like this, to an actual practical system with a kind of dual evaporator and dual condenser heat pump type technologies. And actually, what we're really interested in is, in this autonomous system, can you actually stabilize a system like this, where you are dumping cold into one side and dumping heat into another side, and then using heat pumps and chillers to kind of maintain some kind of stability. And so we are looking at the kind of control systems that you can employ. For example, very simple discrete control like we have with our temperature regulators in the house, or proportional integral derivative control like we use in industrial control, or increasingly in urban environments and in industry, predictive control. So that can be predictive rule-based control or model predictive control. And what we find is that, discrete control only creates a kind of hysteresis in the system. So you can get moderate control of your sink, or actually a better way to call it is reservoir. So we have a hot reservoir and cold reservoir. We really want to stabilize the temperature. Then you can see we get oscillations. But with better control strategies like PID or predictive control, we actually get very good control. With predictive control, we can actually take account of the fact that we might want to have set point variations in our reservoirs over time, because actually sometimes we can anticipate that certain times are going to have higher demand and lower demand, and therefore we can anticipate that and actually take advantage, for example, of cheap electricity. And speaking of that, then we can take these concepts and actually test them also at the site level. So this is at the large building level. Can we employ these techniques? So this is at a supermarket. This is actually some very recent work, but actually, funnily enough, it was inspired by some of the work George did many, many years ago, who was developing machine learning techniques to understand how supermarkets use energy. So supermarkets have increasingly got these cabinets which are closed and which need to be maintained at a certain temperature. So typically between 0 and 4 degrees, but with allowance for some deviation from that over time. So the top graph is showing a typical temperature trace. And what we're looking at here is how we can optimize the operation of these refrigeration systems, so that, for example, you can pre-cool some of your produce. So in the night time, for example, when electricity is cheap, you can go to the lower bound of the set point. And then in the morning, when electricity is more expensive, you can let the system drift to the upper bound. And so here what we're showing is how you can use IoT and cloud computing and some machine learning, because also we measure the air temperature in the cabinet, and then we use a machine learning algorithm to infer what the produce temperature is, because they're not necessarily the same thing. From that, we can make sure that we are always keeping our produce, the so-called CPT temperature, is allowed to drift. And that allows us to reduce energy consumption or to reduce cost, or to some extent both, by employing smart control. So instead of having just on-off control and keeping our produce at its set point, we can cool it more when electricity is cheap, and we can cool it a bit less when electricity is expensive. And actually, cost of electricity correlates quite well with carbon price. So what we see in the bottom diagram is the bars are showing how much money we're saving in the bottom two bars. So sometimes we're losing money against the benchmark, and that's because we are using more electricity when it's cheaper, but overall the bars are positive and they're showing that we're saving. By the way, the grey bars are showing periods when we're defrosting the heat exchangers, because we do need to do periodic defrosting. So let me summarize again. What we're very interested in is how systems approaches and mathematical modeling can help us improve urban energy systems. And we do that by looking at this 4-step hierarchy. What can we do around land use? Now, of course, most of our cities exist, so often our interventions are limited, but actually we do get retrofit, rezoning, or redevelopment opportunities. What I haven't spoken too much about today, because it's a whole topic, is agent-based modeling for people and behavior. How, first of all, you can understand that and to some extent influence it. Then resource flow optimization, where we're looking at how we organize our networks and our technologies and how we can introduce new technologies, for example, like the large-scale ground source reversible gas engine heat pumps in the China example. And then, of course, smart systems. So we jump straight to a very futuristic system with a cold loop and cold reservoir, hot loop and hot reservoir, and constant heat exchange between systems which need cooling and systems which need heating. And so just to summarize, cities provide massive opportunities for climate change mitigation. What's interesting, I think, also is cities at the forefront of innovation. Often cities want to go faster than the nation state, and their governance system allows us to do interventions and to do projects. And tools for the smart design and smart control of urban energy systems are becoming available. And some of those are described in these 2 books that I'm also highlighting here. So thanks very much for your attention, and happy to take any questions.